When thousands of civilians began pouring onto a military base, located on a desert, in the middle of summer, early on a Sunday morning, one could sense the day's events were going to be special. Spectators came to Edwards Air Force Base from all over the nation and all walks of life to celebrate the nation's 206th anniversary of independence and witness historical events more spectacular than the typical 4th of July fireworks display could ever hope to equal. The fourth landing of Space Shuttle Columbia, world's first reusable spacecraft. Columbia's first landing on a concrete runway, officially ending the orbital flight test program. Takeoff of the second orbiter in the shuttle fleet, Challenger, on its ferry flight to Kennedy Space Center, Florida, to be launched into space in the early part of 1983. And with Shuttle Pathfinder Enterprise as backdrop, the announcement of America's new space policy by President Ronald Reagan.
Beginning with the next flight, the Columbia and her sister ships will be fully operational, ready to provide economical and routine access to space for scientific exploration, commercial ventures, and for tasks related to the national security. Simultaneously, we must look aggressively to the future by demonstrating the potential of the shuttle and establishing a more permanent presence in space. Our goals for space are ambitious yet achievable. We've only peered over the edge of our accomplishment.
Surely, our accomplishments began with Columbia's first launch in April 1981.
Roger, roll.
Roll program complete.
Roger, roll complete.
Looking back at that spectacular event and the performance of Space Shuttle during its first 4 flights, there seems little doubt now that it is a reliable, reusable space transportation system. When Columbia first arrived at Kennedy Space Center in March of 1979, there was some skepticism. 2 factors were leading to major delays in the launch schedule. The quest to advance the state-of-the-art in space technology, particularly in engine design and thermal protection, plus budgetary limitations imposed on development and testing of shuttle systems. With 2/3 of shuttle's tiles already on the vehicle, it was discovered that the bond was not strong enough to keep the tiles from falling off during high-stress phases of flight. The fix, called densification, required that most of the tiles be taken off, coated with a material to increase the bonding strength, then reapplied to the vehicle. The process took over 1 year to complete, but it worked. During the orbital flight test program, only undensified tiles showed weakness along their attach points on non-critical areas of the vehicle. Shuttle's main engines achieved the state-of-the-art in rocket engine technology. But as with any research and development program, confidence in the design came only after years of testing, learning, and some mistakes. Problems encountered during development of the engines were related to the unique requirements that had to be met. Reusability, up to 55 flights with minimum maintenance. Ability to throttle down to 65%. Lightweight, yet the capability to withstand extremely high chamber pressure. Pressure needed to generate the thrust for liftoff. Many failures that occurred were due to the tremendous pressures and vibration levels created trying to produce the needed thrust. But one by one, the problems were solved. The design was proven long before the first launch.
Go for auto sequence start. 9, 8, breakers closed. 5, 4, we've gone for main engine start. We have.
Columbia was launched. Again. And again. And again. Four times within 15 months, traveling over 8 million miles during the first 4 flights. "314 revolutions around the Earth. 19 days on orbit. But beyond the statistics, a far more important goal was achieved with completion of the orbital flight test program. The foundation for our future was built, step by step, mission by mission. The goal of STS-1 was, quite simply, to get up and get down safely.
Columbia, Houston, you guys did so good, we're going to let you stay up there for a couple of days. Your go for on orbit.
When astronauts John Young and Robert Crippen heard that announcement, they knew the mission was at least half a success. When returning from space, friction created by entering Earth's atmosphere blocks communication between mission control and the astronauts for 15 to 20 minutes. But it is also precisely during that time that temperatures on the vehicle surface reach their peak and shuttle structure undergoes its most stringent test. On Columbia's first flight, no one could predict exactly how shuttle would perform during that phase.
Hello there, Houston. Columbia's here.
Hello, Columbia, Houston's here. How do you read?
Plan clear, and we're doing Mach 10.
With voice contact reestablished, spacecraft and crew had safely passed through the most critical phase of entry. Landing was the final test.
Right on right slope.
Flown as a glider, Columbia landed without power on the first and only attempt.
You're coming. You're down. 50 feet. 40. 30. 20. 10. 5. 3. 2. 1. Touchdown. Those gears, 10 feet. 5. 4. 3. Touchdown. Houston, Columbia's on the roll.
Welcome home, Columbia. Beautiful, beautiful.
Columbia's second flight was the first opportunity to evaluate the Canadian-built remote manipulator system. Manual functions were tested by astronauts Joe Engel and Richard Truly. Automatic functions were computer-controlled. The arm performed successfully in all operating modes. Preliminary thermal tests of the vehicle were also begun on Flight 2. One thermal attitude resulted in the payload bay being pointed toward Earth for extended periods of time. During those periods, a package of 5 Earth-viewing instruments, designated OSTA-1, was activated. The package, composed of low-cost commercial-grade sensors previously flown only on aircraft, and instruments flown on individual satellites or past manned missions, collected the first Earth resource data using shuttle. The ability to mount all 3 types on Columbia greatly reduced the expense of acquiring the data.
Okay.
100, 50, 30, 20, 10, 5, 3, touchdown. Nose gear 15. 10, 5, 3, touchdown. Welcome home.
Thank you, Chase.
Flight 2 proved shuttle was truly a reusable space transportation system. Third flight of Columbia was primarily a thermal test of the vehicle, exposing it to the most extreme temperature differentials it could encounter on orbit during upcoming operational flights. No facility on Earth could simulate the same heating conditions Columbia would experience in the vacuum of space, where temperatures could vary greatly from one end of the orbiter to the other, depending on its orientation to the sun. The thermal tests determined precisely what effect different attitudes had on shuttle structure. The vehicle suffered no adverse effects. Evaluation of the remote manipulator system continued on Flight 3. Astronauts Jack Lausma and Gordon Fullerton tested the system's payload handling capability. First order of business was unberthing. Although clearance around the payload was only 2 inches, Fullerton unberthed in just 5 minutes, much quicker than had been predicted pre-flight. Using the plasma diagnostics package, 7 computer-controlled automatic movements of the arm were evaluated to prove scientific instruments could be maneuvered in and around the payload bay.
Only some general comments on the arm operation. The operation is smooth. There's definitely a little bit of flex and dynamics, but in the augmented modes, that's very minimized. Really no surprises. If there are any surprises, they're all pleasant. I'm really impressed with that piece of machinery.
Hey, that's great news, and we were impressed too.
The plasma diagnostic package was one of 10 instruments making up a scientific package on Flight 3 called OSS-1. Shuttle's movement through the ionosphere, electrical buildup on surfaces as it circled Earth, and electromagnetic interference between the ionosphere and electronic equipment on board were evaluated by the OSS-1 instruments to ensure that these phenomena would not adversely affect scientific instruments or sensitive astronomy observations on future shuttle flights. On Flight 4, the Induced Environment Contamination Monitor was used to check for contamination in and around the payload bay, created by thruster firings, outgassings, and water dumps. 11 separate components of shuttle's induced environment were measured. The desk-sized monitor was the heaviest payload lifted by the remote manipulator system during the orbital flight test program. Thermal tests on the vehicle were completed during Flight 4. The first Department of Defense payload was on board. The spacesuit to be used for extravehicular activity on Flight 5 was tried on during Flight 4 to practice the procedure. And astronauts T.K. Mattingly and Henry Hartsfield conducted a thorough evaluation of on-orbit procedures for the upcoming operational era of spaceflight, when Columbia will launch into Earth orbit on a routine basis. An ongoing task on all 4 missions of the flight test program was to evaluate living conditions on board shuttle. Items included food preparation, use of a food warmer, a freezer on board Flight 4, and eating in weightlessness. Personal hygiene tasks were evaluated. As were sleeping conditions, use of sleep restraints, and a sleeping bag. Astronauts also evaluated the effects of exercise in zero-G. This unique device, designed by a fellow astronaut, allowed the user to monitor his own heartbeat while jogging. Alternate methods of anchoring oneself in weightlessness were also appraised. Very busy schedules are forecast for upcoming shuttle flights, when crews will be comprised of at least 4 people, including women. Procedures on the ground are being streamlined for the operational era. Processing time was cut in half during the orbital flight test program. Presently, it takes approximately 13 weeks to prepare the space transportation system for launch. It is projected that by the mid-'80s, there will be 2 shuttle launches per month. The number of people in mission control is gradually being reduced. Some positions have been eliminated. Others have been consolidated, which represents a clear indication of confidence in Columbia's systems. While this monitoring is being streamlined, payload monitoring is increasing. A new area called the Payload Operations Control Center was activated during the orbital flight test program to give mission controllers, payload managers, and commercial users the opportunity to develop monitoring and data acquisition procedures for upcoming flights. Experiments in life sciences were carried on board Columbia during the orbital flight test program. A preliminary study of lignin growth in zero-G was conducted. Lignin is an indigestible skeletal substance which promotes strength and upward growth in woody plants. It is hoped that in the absence of gravity, woody plants might not need to produce as much lignin, and instead will produce more digestible nutrients such as carbohydrates and proteins. The effect of weightlessness on some flying insects, bees, moths, and flies was studied. The project, conceived by a high school student, was one of 3 experiments flown on Columbia as part of an annual science competition co-sponsored by NASA and the National Science Teachers Association. Equipment to process materials in zero gravity on future flights underwent initial testing during the orbital flight test program. The monodisperse latex reactor made polystyrene latex microspheres to determine if large identical-sized latex microspheres could be manufactured practically and economically in space. Presently, large microspheres cannot be produced in uniform sizes on the ground. Yet medical and industrial applications have already been found in cancer research and treatment, glaucoma research, and for calibration standards in medical and scientific equipment. The continuous flow electrophoresis system, built by McDonnell Douglas Corporation, is a prototype of a production unit to purify material for the treatment of disease. The process separates substances according to their electrical charge. Hopefully, yields from the production unit will be high enough to make the product available to a mass market in the future. Results from the prototype's first flight show that a very thin, yet highly concentrated stream of protein substance on the left was separated from red dye on the right. The thin protein stream, only a portion of which is shown here, is actually over 43 inches long and is 300 to 400 times more concentrated than yields obtained from the same process on Earth. The continuous flow electrophoresis system represents the first commercial use of shuttle by private enterprise under a joint endeavor agreement between NASA, McDonnell Douglas Corporation, and Ortho Pharmaceuticals Corporation, a subsidiary of Johnson & Johnson. A unique opportunity to put small, self-contained payloads aboard shuttle on a space-available basis at a very low cost exists in the Getaway Special program. After proving its flight readiness on Flight 3, the Getaway Special was fitted with 10 experiments built by science students from Utah State University and flown on Flight 4. Deposits for Getaway Specials on future flights, private enterprises' interest in flying payloads on board shuttle, missions planned into the next decade, all reflect the confidence this nation has in the space transportation system. All objectives of the flight test program were achieved. 2 of the most significant events were not planned. Just prior to the 3rd launch, tons of landing and recovery equipment had to be transported from California to New Mexico, a 1,000-mile journey, because heavy rains in California prevented a landing there. An entire encampment had to be built at the New Mexico landing site, Northrop Strip, and the task had to be completed within 4 days. Just prior to landing on the same mission, only 1.5 hours before touchdown, an unexpected sandstorm blew into the area.
As you could probably surmise, the winds have been coming up all day. It was still acceptable until his last pass, but during John's last pass, the visibilities were unacceptable and the turbulence was severe. So it's not a good day, and we're going to wave off for 24 hours. Over.
Plans were implemented immediately to stay on orbit an extra 24 hours.
We've had a good drill.
The flexibility to remain on orbit until weather conditions improved and land at an alternate strip could not have been demonstrated by previous spacecraft. Only the shuttle has that capability. It meets a need, providing access to low Earth orbit on a routine basis. By launching on time, serving as a platform for Earth observation and space observation, deploying payloads, operating in extreme temperature differentials while on orbit, providing ample living accommodations for astronaut crews, landing on lake beds, or concrete runways. As President Reagan said, the end of the orbital flight test program marks our entrance into a new era. The test flights are over. The groundwork has been laid. Now we will move forward to capitalize on the tremendous potential offered by the ultimate frontier of space. When thousands of civilians began pouring onto a military base located on a desert in the middle of summer, early on a Sunday morning, one could sense the day's events were going to be special. Spectators came to Edwards Air Force Base from all over the nation and all walks of life to celebrate the nation's 206th anniversary of independence and witness historical events more spectacular than the typical 4th of July fireworks display could ever hope to equal. The fourth landing of Space Shuttle Columbia, world's first reusable spacecraft. Columbia's first landing on a concrete runway, officially ending the orbital flight test program. Arrived at Kennedy Space Center in March of 1979, there was some skepticism. Two factors were leading to major delays in the launch schedule. The quest to advance the state-of-the-art in space technology, particularly in engine design and thermal protection, plus budgetary limitations imposed on development and testing of shuttle systems. With two-thirds of shuttle's tiles already on the vehicle, it was discovered that the bond was not strong enough to keep the tiles from falling off during high-stress phases of flight. The fix, called densification, required that most of the tiles be taken off, coated with a material to increase the bonding strength.
Back roll program. Go.
Roger, roll.
Roll program complete.
Roger, roll complete.
Looking back at that spectacular event and the performance of Space Shuttle during its first 4 flights, there seems little doubt now that it is a reliable, reusable space transportation system. When Columbia first arrived, takeoff of the second orbiter in the shuttle fleet, Challenger, on its ferry flight to Kennedy Space Center, Florida, to be launched into space in the early part of 1983. And with Shuttle Pathfinder Enterprise as backdrop, the announcement of America's new space policy by President Ronald Reagan.
Beginning with the next flight, the Columbia and her sister ships will be fully operational, ready to provide economical and routine access to space for scientific exploration, commercial ventures, and for tasks related to the national security. Simultaneously, we must look aggressively to the future by demonstrating the potential of the shuttle and establishing a more permanent presence in space. Our goals for space are ambitious yet achievable. We've only peered over the edge of our accomplishment.
Surely, our accomplishments began with Columbia's first launch in April 1981.